Okay, so now let's look at a more general potential well, right? Because this is obviously the square potential well is something more. It's not a very realistic. So suppose that we take a potential well, which is more like realistic. So how do we deal with that? Let me draw one. So suppose that it's doing something like this, and our energy eigenvalue that we are interested in, we are looking for some energy around that in that region. So how do we deal with this? Well, the answer is to actually do a crude approximation in terms of piecewise constant potential. Okay, so if you have, so we can approximate such a potential through a piecewise constant potential in this fashion. Say, we can say, okay, this is my this is my energy E, and the potential is it does this, it's constant here, and then it goes to 0 here, and then it rises up a little bit here, and then say it rises up more here to the value that, okay? So basically, kind of have a pixelated form of the potential. Okay? So, of course, the kinetic energy is going to be different in different regions here. So here, your particle will have a lot more kinetic energy than over here, right? So we can call this, say, V1. We can call this V2. So in this region, in this region, my wave function will have some form A sine of, say, kx plus phi, where k is not a constant because it'll change its value. So now since both psi and psi prime are required to be continuous, let me just say this is psi prime. Let me call it M, and psi prime is then AK cosine of kx plus phi. Now between, say, psi and psi prime, we can square these two expressions and add them to get rid of the trigonometric functions, and that way we find an expression for the amplitude in terms of psi and its first derivative, which I'm calling m. And there is also k squared coming from here, right? So this you can derive from these two equations. Now, both psi and m, will change continuously. So that means that even when you go from this region to this region, where the value of your kinetic energy changes discontinuously, so both psi and m will change continuously, but k will be discontinuous, right? So this is observation number 1. observation number 2 is that, just from this example, when k decreases, a increases, right? Or k squared decreases, a increases. That means that, the part of my potential, the part where k is small, the amplitude will be larger. Okay? The other thing is that k is related to the wavelength, right? K is the inverse wavelength, right? So, the sine function's wavelength, so the wave function's wavelength, will be modulated according to the value of k. So if k is large, then the wave function, the wavelength will be short. If the k is small, the wavelength will be large. So taking all this into account, we can now sketch what the wave function will be like for this potential. So, in this region, wave function will be exponentially decaying, and then in this region, we'll have oscillatory wave function. But when it enters this region, what will happen is that the wavelength will become larger, right? And since k is decreased, the wavelength will be increased, right? So we'll get something like this. Okay? So this is basically what allows us to sketch wave functions for a given energy. So let's end this class with another one, which is a linear wave function, a linear potential. So if I take a linear, sorry, not like this. Suppose I have a wave function like this, a potential like this. Right? So we can think of such a potential as being, say, made out of small steps. Okay. And then using the heuristics that we just developed, we have, so for example, we have to choose some energy, say E, and over here, K is large, and therefore my amplitude will be small, as well as my wavelength. So, and so it'll be something like this, okay? So these are the heuristics. So I want to end this section by talking about some symmetry consideration, but before we do that, do we have any questions?
Sir, you said that the wavelength would be modulated. Shouldn't it be that the amplitude is modulated?
Both, right?
Oh.
Both.
But
In
wavelength.
case,
Sorry.
yeah. Because K it gives you 1 over lambda, right?
Right.
So, and K squared gives you Not it's in not it's not inverse, but it's 1 over a as well, right?
Yeah. Okay, I see.
It's a different functional relationship, but they're both kind of here. Okay, so any more questions? Okay, so let's conclude this class with a few comments about symmetry considerations. So suppose we have a potential which has a symmetry axis, okay? Say, suppose V of x has a symmetry axis. So we can choose our coordinate system in such a way that V of the axis is at x equals to 0. So V of x is equals to V of minus x. So examples are like this. So for example, we can have a quadratic potential, or we could have a quartic potential with a with a constant such that we have something like this. Okay, so these are both have symmetries. So for such potentials, it's easy to see that the wave functions, the energy eigenstates, the energy eigenstates have definite parity. That is, they will either be of this form, psi minus x is equals to psi of x, or psi minus x will be equal to minus psi minus of x. Okay. And how do we derive this? We derive this very easily because, if it's symmetric, then we see that, the probability of the particle being, say being here or here should be the same, here and here, right? They should be the same for static cases, which means that psi of x whole squared should be equal to psi of minus x whole squared. And there are two solutions to this one and this one. Okay, so this is basically for symmetric potential, that's the case. So this is all I had to say about how to heuristically think about one-dimensional potential. So should I summarize it here, or should I postpone the summarization until the next class? Maybe, yeah, do a summary and we can review it, okay? So for the summary is that for one-dimensional potential, for 1D bound states, the nth energy eigenfunction has n minus 1 modes, or nodes, sorry, not modes. Say nodes on the finite part of x-axis plus 2 zeros and infinity, right? That's number one. Number two is that the wave function in the region of positive kinetic energy concaves towards the x-axis. Towards the x-axis, okay? And number 3 is that the opposite, wave function in region of negative kinetic energy concaves away from the x-axis number 4 is that the conditions of psi and psi prime to be continuous puts strong constraints on the solutions. Number 5 is that if k squared is large, wave functions have definite symmetry. Okay, so this is it. Any other questions?
Sir, I think I missed part 5 and 6 due to some internet problems.
So 5 and 6.
Yes.
Well, what was the question? You missed it?
Yeah, the part. Like
Okay,
number part
just
6.
1 second. Okay, let me just rejoin with the other screen. So I have, yeah, okay. So what happened with 5 is that, we found that psi is, say, a sine of kx plus, say, phi. And so psi prime is ak cosine of kx plus phi. So then what we say is that, well, if I do psi squared plus, say, let's call this m squared by k, then I have a squared, right? So a is essentially going to be square root of psi squared plus m squared by k squared. So that means that where k, the kinetic energy is large, the amplitude is small. So part of the potential, if the potential is like this, and this is your total energy, the difference between the total energy and your potential energy is the kinetic energy, right? So in this region, kinetic energy is very large. So if the kinetic energy is very large, the amplitude there is small. And here, the kinetic energy is small, and therefore the amplitude is large. So that is one thing. The other thing is that k is also the wave number. So roughly speaking, k is given by 2 pi by the local lambda. Okay? So if k is large, then the wavelength is small. If k is small, the wavelength is large. So those are the things that we took into account. And for example, we derived, say, this wave function, right? Here, the kinetic energy is small here, the wavelength is large, as well as the amplitude is large. The kinetic energy is large here, the wavelength is small, the amplitude is small, okay?
Yeah, okay.
Okay, any other questions?
No, sir.
Well, if not, okay, so the next, the quiz will be on 28th, not tomorrow. Okay, so thank you very much. I will see you day after tomorrow, right?
Sir, won't you take attendance?
Oh, yeah. That's a good idea. I guess I should, because I've been having so many unusual times that I can keep forgetting. But you're right. Thank you. We should do the attendance today. Yeah. I will be pretty relaxed about attendance this semester, so you're probably going to get there 5% for free. Okay, Isa, are you there?
Yes, sir.
Jabbar? Tuhin? Sheikh? Is that a yes or no? Okay, that's a yes, I guess. Zabir?
Yes, sir.
Okay, Nafis?
Present, sir.
Okay. Mashikur? Okay, Nusaiba?
Present, sir.
Okay, that was probably Mashikur, right?
Yes, sir.
Nusaiba? Okay. Dipro?
Yes, sir.
Good. Medat?
Sir, I think Musaiba is present. She can't respond because she doesn't have a mic.
Okay, no worries. Yeah. Okay, what about Yeshan?
Present, sir.
Okay, good. Ibnat Anand Chaudhary?
Yes, sir.
Okay. Shujosh is there. Okay.
Yes, sir.
Sitima?
Present, sir.
Good. Ibnul Ahsan Mayuk? Audrey? Saif is there, right?
Present, yeah.
Mahmoud Abdullah? Samia Hamid? Nian is there, I think.
Present, sir.
Otonu? Okay. Farhan is there.
Yes, sir.
Ushik? Okay. Sumaya? Okay.
Yes, sir.
Proma?
Uh.
Okay, awesome. Thank you so much.
Thank you, sir.
Yeah, okay. Have a good evening.
Okay, thank you, sir.
Sir,
Goodbye.
Assalamualaikum.
Yeah, Studin, I got you. Yeah.
Thank you, sir.
Assalamualaikum, sir.
Walaikum salam.